Hello, and welcome back to another lesson in thermodynamics. We are still on the unit on temperature and heat. So in our previous lessons, we have discussed about uh, thermal expansion, wherein uh, a material will expand when subjected to changes in temperature due to application of heat. And the amount of expansion is usually dependent on the specific heat value of that certain material. We also have discussed in the previous lesson regarding the quantity of heat and temperature changes. So we quantified how we measure the heat absorbed or the heat released by an object when uh, its temperature changes. So for this lesson, we will be uh, talking about what is the quantity of heat involved in phase changes, and that study is basically called calorimetry. So we'll explore uh, calorimetry problems and its applications. So phase change is basically just the change of state of matter. So it's either from solid to liquid or liquid to gas. So solid to liquid transformations are usually termed as fusion, and liquid to gas transformations are usually referred to as vaporization. So usually phase changes happens at the freezing points and the boiling points. So freezing points for solid to liquid transformations, boiling point for liquid to gas transformations. So for instance, you have a solid ice at 0 degrees Celsius. It can become liquid water at the same temperature, 0 degrees Celsius, if it absorbs heat. So usually we call this process melting. So it absorbs heat and the ice melts, but it's still at the same temperature at the freezing point, 0 degrees Celsius. So in a phase change, there is no temperature change. So if the liquid further absorbs heat, if the liquid water further absorbs heat, then it can change its temperature from 0 degrees Celsius and say to the boiling point, which is 100 degrees Celsius. And when it further absorbs heat, that is usually what we term as evaporation. That's another phase change, wherein the liquid water at 100 degrees Celsius becomes gas or water vapor at the same temperature, 100 degrees Celsius. So again, there's no temperature change in a phase change. So the reverse from gas to liquid water at the same temperature is what we call condensation, and that usually involves releasing of heat or removal of heat. So the liquid water can then undergo a temperature change by releasing heat. So it can undergo a decrease in temperatures from 100 to 0 degrees Celsius. And if when it further releases heat from its liquid state, liquid water at 0 degrees Celsius, it can become solid ice at 0 degrees Celsius at the freezing point. So usually we call this term, or they call this transformation as freezing, the reverse of melting. But melting and freezing are generally referred to as fusion, and evaporation and condensation are generally referred to as vaporization. So the amount of heat needed in phase changes depends on the uh, type of material, similar to the amount of heat in temperature changes. But in the case of a phase change, there's now a different constant called the latent heat with a symbol L. So if an object with mass m and a constant latent heat L, if it absorbs or releases heat at a certain freezing point temperature or boiling point temperature, then it will still remain in that temperature, but its phase will now change, say from solid to liquid or liquid to gas. So the amount of heat needed to change the state of the object depends on the mass of the object and the latent heat. So L is similar to the specific heat. It's just a different property of a material. So as of this point, a material can now have a coefficient of linear expansion, coefficient of volume expansion, specific heat, and this one, the latent heat. So you will notice that there's a plus and minus here. You use the plus formula if the heat is absorbed by the body. You use the minus formula if the heat is released by the body or the object. So solid to liquid transformations are usually called fusion, and the latent heat involved in that is the latent heat of fusion, the subscript LF or F. And liquid to gas transformations are usually referred to as vaporization, and the latent heat involved in that is the latent heat of vaporization, L. So these are the different latent heat values for different materials. So the first column is the melting point of the material in Kelvin, and the second column is the melting point of the material in degrees Celsius. And these are the latent heat of fusion values, and these are the latent heat of vaporization values. So these are the boiling point temperature here, these columns here. So for water, for instance, its freezing point is 0 degrees Celsius or 273.15 Kelvin. And the heat of fusion is, latent heat of fusion is 334 times 10 to the 3. The unit is joules per kilograms. So the boiling point of water is 100 degrees Celsius, or that is 373.15 Kelvin. And the latent heat of vaporization, LV, is 2,256 times 10 to the 3 joules per kilogram. So you will notice that it's easier to melt ice or water as compared to boiling it. It's easier to freeze as compared to boiling it. So fusion transformations usually require lesser heat as compared to vaporization. So you will notice in the pattern here, the heat of fusion values are usually much lesser or smaller as compared to the heat of vaporization values. This is just another example. You have ethanol. This is the melting point of ethanol, negative 114 degrees Celsius. Its boiling point is 78 degrees Celsius. So in general, the study of measuring heat involved in phase changes and temperature changes is what we call calorimetry. So in the previous lesson, we discussed about the quantity of heat and temperature changes. That's actually the start of calorimetry. So a calorimeter is a device used to measure heat and the specific heat of materials. So usually it's a thermally insulated material, such as a thermos bottle or a styrofoam cup. So usually you place an unknown material inside your calorimeter and try to measure its specific heat by performing an experiment. So if a system is thermally insulated, or what we call thermally isolated, heat is actually conserved. When heat is conserved, the total amount of heat within that system is zero, meaning there is no heat lost to the surroundings, or there's no heat exchange with the surroundings. And the heat exchange is only within the contents of your calorimeter. So if there's a hot object there, that hot object will release heat. And if there's a cold object there, that cold object will absorb that heat. So what the total heat is conserved, and the total heat is zero. Okay. So let's now have an example, an application of calorimetry. So this example is called freezing water to ice. So how much heat must be removed from water with mass of 0.10 kilogram and temperature of 10 degrees Celsius to make it ice at negative 10 degrees Celsius? So usually, the one removing heat is what we call a freezer. So usually when you put material in your freezer, the freezer absorbs the heat, or is the one removing the heat from your material. So initially, you have liquid water at 10 degrees Celsius, and your final material is solid ice at negative 10 degrees Celsius. Now, this doesn't happen in one step. So first, the liquid water at 10 degrees Celsius must undergo or must release heat in order to undergo a temperature change from 10 degrees Celsius to 0 degrees Celsius, which is the freezing point of the water. So from this point, the liquid water at 0 degrees Celsius will further release heat to undergo a phase change from liquid to solid, but again at the same temperature. This is a phase change. And finally, the solid ice at 0 degrees Celsius will again release heat to further undergo a temperature change from 0 degrees Celsius to negative 10 degrees Celsius. So you will notice that there are three heats here, or there are three stages here, and each stage corresponds to a released uh, amount or quantity of heat, Q1, Q2, and Q3. And the total heat Q that must be removed from water to make it ice at negative 10 degrees Celsius is just the sum of these three heats, or amount of heats. So for Q1, it's a temperature change. So the formula is MC delta T. So this is water, so you need to use that specific heat of water, which is 4190 joules per kilogram Celsius degree. The change in temperature of the water is the final is 0, the initial is 10. So 0 minus 10. So the mass is 0.10 kilograms. So you will get negative 4190 joules. So your answer should be negative because this is heat released by the body. So for Q2, Q2 is a phase change, meaning the formula is negative MLF. We use the negative formula because this is heat released by the object or by the body. So the latent heat of fusion for water is 334 times 10 to the 3 joules per kilogram times 10.10 kilograms, and you will get negative 33,400 joules. Lastly, the last stage is a temperature change. So you use MC delta T formula. But take note that this is now ice, and ice has a different specific heat as compared to water. Specific heat of ice is 2,100 joules per kilogram Celsius degree. So the final temperature is negative 10, the initial temperature is 0, and you will get negative 2,100 joules. So the total heat involved in making liquid water at 10 degrees Celsius to becoming solid ice at negative 10 degrees Celsius will then be the sum of these three amounts of heat or quantity of heats, and you will get a value of negative 39,000 joules or negative 39.69 kilojoules. So that's it. That's it. So this is calorimetry. It's a combination of temperature changes and phase changes. So let's have another example. So this is now boiling ice. So how much heat must be absorbed by 0.10 kilogram ice at negative 10 degrees Celsius to start boiling? So our starting point here is solid ice at negative 10 degrees Celsius. Our final final product or final material is liquid water at 100 degrees Celsius. So this is the point wherein water starts to boil, liquid water at 100 degrees Celsius. So there are, again, more than one step involved in this transformation process. So first, the solid ice at negative 10 degrees Celsius will absorb heat to undergo a temperature change from negative 10 degrees Celsius to 0 degrees Celsius. And then the solid ice at 0 degrees Celsius will further absorb heat to undergo a phase change to become liquid water at 0 degrees Celsius. And finally, the liquid water at 0 degrees Celsius will absorb an additional amount of heat to undergo a temperature change from 0 degrees Celsius to 100 degrees Celsius. So similar with the previous example, the total heat absorbed is just Q1 plus Q2 plus Q3. So Q1 is a temperature change, or meaning the formula is MC delta T. Again, this is ice, so you use the specific heat of ice, and you will get a positive result. So here, the final temperature is 0 minus the initial temperature, which is negative 10. So you will have 0 plus 10 here. So all of your answers here must be positive because this is heat absorbed by the body. So Q2 is a phase change. So it's a fusion from solid to liquid. So you use the positive ML formula because this is absorbing heat. So you will get a value of 33,400 joules. And lastly, Q3 is a temperature change from 0 to 100. So since the state involved here is now a liquid water, then you use the specific heat of water, which is 4190 joules per kilogram Celsius degree. The final temperature is 100 degrees Celsius, the initial temperature is 0 degrees Celsius, and you will get a value of 41,900 joules. So you add all of these three to get the total absorbed heat, which is 77,000 or 77.4 kilojoules. Okay. So for our last example, we will our last example will involve a calorimeter. This is a typical experiment in calorimetry. So a laboratory technician drops a 0.0850 kilogram sample of unknown material at a temperature of 100 degrees Celsius into a calorimeter. So the calorimeter can, initially at 19 degrees Celsius, is made of 0.15 kilogram or 0.150 kilograms of copper and contains 0.200 kilograms of water. So basically, you have a calorimeter can, and it contains water, and the can is made of copper. So assuming thermal equilibrium, this temperature of 19 degrees Celsius is the initial temperature of the water and the copper calorimeter can. And then you drop a sample with initial temperature of 100 degrees Celsius and mass of 0.0850 kilogram into the calorimeter, and after thermal equilibrium, after a certain time, all of the three, the sample, the copper calorimeter can, and the water have the same final temperature. They have undergone thermal equilibrium. So the final temperature of the calorimeter can and the contents is 25.43 degrees Celsius. So compute the specific heat of the sample and what is the sample. So what happens here is there's no heat exchange with the surroundings, meaning the total heat within the calorimeter can is 0. So the sample releases heat, and this heat is absorbed or divided or absorbed by the water and the copper calorimeter can. So the total heat is just the heat released by the sample, the heat absorbed by the water, plus the heat absorbed by the calorimeter can. So this term here is negative because this is heat released by the sample. This is positive because this is heat absorbed by water, and this is positive because this is heat absorbed by the calorimeter copper can. And if you add all of these three, you will get 0 because the heat is conserved. So since there are no phase changes involved here, or there are no phase changes mentioned, then only temperature change is present. So this is the temperature change or quantity of heat for the temperature change of the sample. So mass of the sample, C of the sample, change in temperature of the sample. So they all have the same final temperature, but the initial temperature of the sample is 100 degrees Celsius. So this is the heat absorbed by the water. The final temperature of the water is this the same, the final temperature of the sample. But the initial temperature of the water is just the same as the initial temperature of the copper calorimeter can, which is 19 degrees Celsius. So this is specific heat of water, specific heat of the copper calorimeter can. So all of these values are given except for this value, the specific heat of the sample. And that's actually what we are trying to find. So solve for the specific heat of the sample. So do some algebra manipulation. So cross multiply, transpose, group similar terms to solve for specific heat of the sample. And you will get this equation. So you substitute. So all of these values here are already given in the problem. And you will get a value of 909.45 joules per kilogram Kelvin or joules per kilogram Celsius degree. And this is very close to the specific heat of aluminum, which is 910 joules per kilogram Kelvin. Therefore, this sample must be an aluminum material. So that's it. That is one example or one application of calorimetry or a calorimeter count. So this is if we had a face-to-face laboratory, we can perform this activity. And that is it for this lesson. So I hope you have learned something about calorimetry and phase changes and temperature changes. And I will see you again in the next lessons. Goodbye.